we're getting into the reactions of the benzene compounds. So we had discussed quite a bit how these benzene compounds are rather reluctant to do normal alkene reactions. So all of those addition reactions that you learned last semester with regards to the alkenes, addition of HBr, addition to Br2, all of that stuff, these benzene compounds do not do, because if they were to do that, they would become non-aromatic. And as we discussed in the last chapter, those reactions that take a species from an aromatic state to a non, or even worse, anti-aromatic state are generally incredibly difficult to do. So the new type of mechanism that we had introduced at the end of last lecture was this electrophilic aromatic substitution mechanism. And the benefit of that is that it allows the benzene rings to react, and it allows them to retain their aromaticity, simply substituting a benzene hydrogen for whatever group you happen to be putting on, right? So the example that we looked at last time was the halogenation. And what we had said was the first step in virtually all of these mechanisms was going to involve the formation of a very, very strong electrophile, right? And so in the case of the halogenation reaction, we're going to add the molecular halogen that you're trying to put on the ring, whether that's chlorine or bromine or iodine. But in addition to that, because the molecular halogen is not nearly electrophilic enough, we're going to add a Lewis acid catalyst. And that Lewis acid catalyst, the point of it is to essentially pick off one of those halogen atoms. So if you imagine combining the Br2 with the Lewis acid, what you end up making from that is actually, this is a bit of an oversimplification, but for mechanism purposes, it makes things a little bit easier. You can kind of think of it as something like that. So we're generating, and you'll notice that the Lewis acid ended up kind of picking off one of the bromine atoms from the molecular halogen. And as a result, you're left with this Br plus species. And as we talked about last time, these halogens are quite electronegative. Right? They're on the very right-hand side of the periodic table, very, very electronegative atoms. And as a result, if they are forced to bear a positive charge, they are incredibly unhappy. And so they are going to be looking for electrons, any electrons that they can get their hands on. And there just happens to be a nice rich reservoir right in that benzene ring. And so the first step of all of these mechanisms is the pi electrons of benzene go out to attack that super powerful electrophile. That should result in that high energy, positively charged intermediate, which we term the sigma complex. And then in the next step, we said that usually some sort of a conjugate base is going to come in, grab a proton. Those electrons go back into the ring and ultimately restore the aromaticity of the benzene. And again, what you're left with at the end of all of these is simply substituting a benzene hydrogen for whatever is the electrophile you generate. Okay? Does anybody have questions on either the generalized EAS mechanism or this specific reaction? Okay, if not, then I think, did I give you the table of what other halogens you could put on and the conditions that you would use to do that? Mm-hmm. Okay, all right. So we can now put on a halogen on the benzene. So what? Why is that useful? What in the world could we ever do with a halogenated benzene?
Make it greener.
Yeah, exactly. If you think about it right now, organic synthesis, the goal of organic synthesis is making carbon-carbon bonds. because we're trying to make organic molecules, which are made of obviously carbon-carbon bonds. And at this point, you really only have a couple good ways of doing that. And for synthesis at this stage anyway, the Grignard is going to be your workhorse. Okay, it is going to be the most common way that you go about making carbon-carbon bonds as you begin to assemble your molecules. Right? Now, that means if you're going to use the Grignard chemistry, you need two pieces, because a Grignard always involves combining two things, namely a halide, either alkyl or aryl, and a carbonyl group. Right? So if you're going to try to use Grignard chemistry to incorporate these benzene rings into your molecules, you're going to need to somehow be able to either put a carbonyl on it, which we'll talk about later, or put on a halogen. And so through this chemistry, this gives us a really nice way of making halogenated benzene rings that could then potentially be used for Grignard chemistry. So for instance, if we were going to use that to do Grignard chemistry, we could take that bromobenzene that we just synthesized. I could use magnesium, so the magnesium inserts itself and it essentially generates a carbanion-like species, right? So you can imagine, once you add the magnesium here, the benzene ring is effectively going to behave as if it is like that, right? Where it essentially puts a negative charge where the halogen is. And then that's our nucleophile, so we need to throw in an electrophile. Just use a really simple one. And so mechanistically, the way this works is the halogen, again, is going to act as a carbanion to attack the carbonyl, which is going to give us initially something that looks like this. And if you recall, at the end of every Grignard reaction, you always have to do an H+ step. And the reason we always have to do that is because if you want to isolate a neutral compound, you have to provide the H for this alkoxide, right? So just at the end of every Grignard, we always do a final H+ step, and that will convert that alkoxide to a neutral alcohol. Okay. Any questions on this? Okay, then let's look at the next one. What else can we do on these benzene rings? The next thing we can do is we can think about putting nitro groups on the ring. So we can do a nitration here. So this is going to start the same way, starting with my benzene. If I'm going to put a nitro group on the ring, we have to somehow, again, generate a super potent electrophile. And the way we're going to do that in this reaction is through the combination of two concentrated acids, namely concentrated nitric and concentrated sulfuric. So let's have a look and see what exactly is happening as we combine these very strong acids with one another. So if you think about the Lewis structure of nitric acid, it's going to look something like this. Okay. HNO3. So what we're going to do now is add sulfuric acid to this. So I'm just going to kind of abbreviate it as H+. So what do you think is going to happen here? What is the point of adding H+ to this nitric acid? What is the point of adding any acid to anything?
be co-emitter?
Yeah, strong acid is a proton donor, so it would make sense that the sulfuric acid is going to donate a proton. And so we can mechanistically kind of draw it like this. Have that oxygen go and grab a proton. That species would end up looking then like this. What do we do, by the way, by protonating that oxygen with the nitric acid? What have we done? Yeah, exactly. Anytime you protonate an OH group, you're always doing it for one purpose, and that is to make a good leaving group. And so at this point, the species that we made, you might notice, is terribly unstable because you've got those two positive charges right next to one another. And so as a result, it's really looking to alleviate that. You can draw the arrows like this, where the lone pair from an oxygen push in and help to push out that water. So we generate water from that, but more importantly, we generate this NO2 plus species, which is known as the nitronium ion. And it is this nitronium that is your super potent electrophile that will ultimately coax the pi electrons out of benzene to attack it. So let's go ahead and see what that's going to look like. So once you, oh, by the way, you'll note all of these, both of these steps that I've drawn here, I have at equilibrium. And this has some practical implications for doing this reaction. You see why it might not be such a good idea. You're going to actually go and do this reaction momentarily, well, in an hour or so. So do you see why it might not be such a good idea to take your Erlenmeyer flask or your round bottom, whatever you decide to use to run the reaction in, and wash it really well before you start this reaction? Do you see why having a bunch of excess water around might not be such a great idea for this process? Yeah, exactly. If you've got a bunch of, so think of it, it's a Le Chatelier thing. So if you have a bunch of this, or either one of these around, it's going to push the equilibrium in the reverse direction. Saying it another way, if you have a bunch of water around, it's just going to react with your electrophile. So the practical implications of that is, when you go to run this reaction, don't wash your glassware beforehand. Try to make everything as dry as you possibly can so that you don't kill your electrophile. Right? So in any case, once we have generated the nitronium, maybe down here, the pi electrons go out of the benzene to attack. And that's going to generate that high energy sigma complex. Like that. And then, as with all of these, the second half is some sort of a conjugate base. In this case, it would be either water or bisulfate. Some conjugate is going to come in, grab the proton, and restore the aromaticity of the ring. So your final product looks something like that. Okay. Any questions about the nitration here? All right, so what would we ever use this for? Well, to be honest, nitrobenzenes are not all that useful in and of themselves. However, we can do further chemistry with nitrobenzenes that get us access to very useful compounds. It turns out that these nitro groups are very easy to reduce. So we can take them take a nitrobenzene, and through a bunch of different reagents we can reduce them. So you can take a nitrobenzene and you can treat it with, say, LAH, so lithium aluminum hydride, or you can use catalytic hydrogenation, or you could use transition metal in acid, so something like tin or iron in HCl. All of these will end up reducing the nitro group to the aniline. And these aniline compounds are very, very useful because they're found in a lot of things. Now, sometimes it's just as useful to know what won't work as what will work. So I do want to show you, so I've given you 3 different conditions that will reduce the nitro to the aniline. I want to show you one that will not. And that would be sodium borohydride. Sodium borohydride will not reduce the nitro to the aniline. But that's also useful to know. So for instance, why would that be useful? Well, let's say we wanted to do this reaction. So do you see how in this example, it might be useful to know that. Right? I mean, what would be the risk of trying to do this transformation with LAH?
You'll reduce the carbonyl and the
Yeah, exactly. I mean, yeah, LAH is going to reduce the ketone to the alcohol for sure, but LAH is a sledgehammer of a reducing agent. It's going to reduce anything and everything. And so when you have 2 different groups, like the ketone and the nitro group, one of which you want to keep, one of which you want to reduce, you have to be kind of selective about what conditions you use. All right? So in a case like this, our best bet would probably be to use borohydride, because we know it can reduce aldehydes and ketones, but as we just discussed, it cannot reduce aromatic nitro groups. Any questions on this one? All right, then let's go ahead to the next thing we can do with these. So we can sulfonate the ring. And this is going to involve making a class of compounds that are known as benzene sulfonic acids. So for instance, we can take benzene, and what we're going to use is sulfuric acid, but we're going to add a little bit of something extra. And that something extra is sulfur trioxide, about 8%. And this makes what is oftentimes called fuming sulfuric acid. Right? So sulfur trioxide is a nice white powder, and if you throw it in sulfuric acid, it begins to smoke or fume, and hence its name. So what we're going to make here, I'll show you the mechanism momentarily, but this is going to end up making a benzene sulfonic acid, which looks like this. So let's see how we make our potent electrophile in this case. So sulfur trioxide looks like this. Now wait a second. Did I just have a stroke? Is that reasonable, what I just did here? I've got, by my count, 12 electrons on sulfur. Is that okay? Yeah, remember, once you get to a certain level in the periodic table, atoms can expand their octets, right? And it's usually once you get to group 3 and below, because the atoms get access to those d orbitals, right? Now, normally in organic chemistry, we don't care about any of that because it's primarily metals, and we don't care about metals. So there's two common examples that we'll see of atoms that expand their octet in organic chemistry, and that's going to be sulfur, that can make a total of 6 bonds, and also phosphorus, which will commonly make 5 bonds. But other than that, we really don't care about expanded octets. Those are really the only two common cases you're going to see in organic chemistry. All right? But in any case, once we add sulfuric acid to this, well, not surprisingly, it's going to protonate something. And what it will protonate is one of those oxygens to give us something like this. So that would be one resonance form. I could also do the other one. And ask yourself, of the two resonance forms that I drew, which one is better? Which one is more highly contributing? The one on the left or the one on the right? It's basically a matter of the positive charge can be either on an oxygen or on a sulfur. What's better?
That one's better.
Yeah, why is that?
Because oxygen's more alternative.
Yep, exactly. So remember, when you have a choice of putting a positive charge on two atoms, the one that is less electronegative will be more likely to bear the charge, right? Oxygen is a lot more electronegative. That means it is less capable of handling a positive charge than something like sulfur that is less electronegative, right? So this would be the more highly contributing resonance form as a result. And that's the one that we'll use for the mechanism here. So you've got a electropositive sulfur. And that is what the pi electrons are going to attack. And again, all that does is it makes that sigma complex. Like that. And then again, the conjugate can come in and take the base, or the proton rather, and restore the aromaticity. Does anybody have questions on this mechanism? All right, so what is the point of these? Well, they can be used, they have some kind of practical applications in terms of the types of compounds that they can make. So you can use these benzene sulfonic acids to make a class, an important class of antibiotics called the sulfonamide antibiotics. You can use these in the synthesis of detergents. So if you turn over your shampoo bottle, for instance, at home, you'll see the primary ingredient is either sodium lauryl sulfate or sodium lauric sulfate. Well, both of those involve, the synthesis of them involve with a benzene sulfonic acid compound. So they're used commonly in the synthesis of detergents. But what we're going to be using them for in a synthetic sense is we can take them and subject them to something that's called molten fusion. And what that does is you take the benzene sulfonic acid, and you put it in liquid sodium hydroxide. So I'm not talking about a solution of sodium hydroxide, I'm talking about liquefying sodium hydroxide. So if you think about that, sodium hydroxide is a salt. It's like sodium chloride. So what we're going to have to do if we want to convert this solid salt into a liquid is we're going to have to heat it to a very, very high temperature. So somewhere between 350 and 400 degrees Celsius. And what that does is it initially converts the benzene sulfonic acid to a phenoxide, which can then be protonated to give us phenols. Now, you should be aware that this sodium hydroxide at 350 degrees is not exactly mild conditions. These conditions will wreck a lot of functionality. You know, if you had an ester, let's say, the chances of an ester surviving the molten fusion conditions would be less than 0. Right? So these conditions, these very, very hot, very, very basic conditions are going to destroy a lot of functional groups. So the point I'm trying to make is if you're going to try to use this in synthesis, use it early on. Don't wait until the end of your synthesis and throw this in there at the end, because a lot of your functionality will get destroyed under these conditions. All right? So use that to help plan synthesis. If you're going to use molten fusion, try to do it early on when you don't have a lot of extraneous functionality. All right? Now, we'll learn later in a different unit kind of a kinder and gentler way of making phenols, but for now, this is the only way we've got. All right? The other thing that you can do with these benzene sulfonic acids is the reverse reaction. So you can take a benzene sulfonic acid and in dilute acid, you can remove them. So you might be asking yourself, well, why would I go through the trouble of putting it on if I'm just going to take it off? You'll see, we'll get into this conversation on Wednesday this week, but these sulfonic acid groups, they have interesting directing effects. And so you can put them on, use them for this particular directing effect, and then take them back off. So, like I said, we'll talk about that in more detail on Wednesday. But just be aware that you can both put these guys on and take them off if you wanted to. All right. Any questions about the sulfonations? Okay, so then up to this point, we've been talking about what kind of, let's say, decorative groups we can put on the ring. You know, halogens, nitro, sulfonic acid groups. It would be nice if we could use this chemistry to put carbon groups on the ring. And that's what we're gonna get into now. After all, making carbon-carbon bonds is the meat and potatoes of organic chemistry. And so it would be nice if we could use some of this chemistry to do just that. And so these next three variations all fall under an umbrella that are known as the Friedel-Crafts reactions. And the first one, I'll call this A, is where we'll look at the Friedel-Crafts alkylation. And so to do Friedel-Crafts alkylation, we're going to be using an alkyl halide. So let's say chloroethane. But we need to do something to make this a much better electrophile. If you just throw chloroethane and benzene together, absolutely nothing's going to happen. So we're going to borrow a trick that we used earlier. To make this a much stronger electrophile, we're going to also add in a Lewis acid. And its purpose is exactly the same. In the same way that when you added a molecular halogen to a Lewis acid, the Lewis acid effectively just plucked off the halogen from the molecular halogen. It's going to do the exact same thing here. If you take a Lewis acid and put it in the presence of a alkyl halide, the Lewis acid is just going to pluck off that chlorine. All right? And so, again, this is a bit of an oversimplification, but if you mix those two together, you will end up making AlCl4 minus, and then, more importantly, a carbocation. And you all know at this point how reactive carbocations are. They're very, very electron deficient species that will take electrons anywhere they can find them. And again, there happens to be that very rich area, high electrons. And so in the first step, the pi electrons go out to attack the carbocation. So now our 2-carbon ethyl group is attached to the ring in this high energy sigma complex. And then the conjugate, the AlCl4 minus, comes in to grab that proton. And in the end, you end up with the ethyl group substituted onto the benzene ring. Now, as before, you also, if you kind of keep track of your atoms, you would make HAlCl4 minus, or sorry, neutral HAlCl4. This rapidly decomposes. And so we do regenerate that catalyst. But the important thing is that you take the benzene ring, through the combination of these two reagents, you end up with the alkyl group substituted onto the benzene.
Professor, so does this only work with primary or methyl alkyl halides, or?
Hold on to that question for just a minute, because that is something we need to address. Okay. Any other questions on this reaction or mechanism right now? Okay, now there are some limitations that you should be aware of in this reaction. So number one is polyalkylation. So when we were discussing Diels-Alder chemistry, we talked about electron donor groups and electron withdrawing groups in the context of dienes needed to be electron rich to be very reactive, and so we typically substituted them with the donor groups. Dienophiles needed to be electron poor, so we typically substituted them with withdrawing groups. And that's why many of our dienophiles had carbonyls or nitro groups or things like that to pull electron density out of the dienophile. Right? So where this comes into play here is that alkyl groups are electron donor groups. But this is the whole source of carbocation stability. Right, if you think about it, why is a tertiary carbocation more stable than a primary carbocation? Well, because it's more highly substituted. And those extra alkyl groups can push electron density into the carbocation and help stabilize it. So this is just repeating something you already at some level knew, that alkyl groups through induction are electron donor groups. So where that comes into play is, think about that reaction we just did. You took a benzene, through the addition of the alkyl halide and the Lewis acid, we substituted the benzene ring. So the question, what's more reactive? Or I guess maybe another way of phrasing that is, which ring is more electron rich? The reactant or the product? The product, right? The reactant has no substituents at all. The product has an alkyl group, which are electron donor groups. So by that logic, the product is more electron rich and thus more reactive. I mean, think about what the first step of this mechanism is. The first step of the mechanism is the pi electrons going out to attack an electrophile. So the more electron density is in this ring, the more reactive the ring will be. And you're going to see this crop up several times through the semester. In cases where a product is more reactive than a reactant, it's usually not a great thing for reactivity, because it gives a competition. Well, this guy can go react with the reagents, or this guy can go and react with the reagents. Well, this one is more reactive, so it's going to react faster. And so if that were to happen, we would make that. What's more reactive, this dialkyl or the monoalkyl? It's got to be this one, because this has two electron donating groups and this one only has one. So we make this. Well, what's more reactive? So you see where we're going with this? It's kind of like a chain reaction, where each product that you make is more reactive than its predecessor. And that leads to a mess, is what it leads to. Just a whole bunch of different alkylated products. Now you can get around this through playing around with stoichiometry. So if I use just a whole bunch of excess benzene, just statistics would override, where the likelihood of encountering an ethyl benzene versus a benzene is just, it's just going to encounter the benzene so much more often because there's so much more of it. So you can get around this a little bit by playing around with the amounts that you use, which would be fine if you were just using benzene. I mean, you can buy a jug of benzene for cheap. It doesn't matter if you have to use a bunch of excess. But if you had been working on some benzene ring and this was a highly decorated ring and you'd already done like 5 steps previous in your synthesis, you're not going to want to use a whole bunch of excess of it just to throw away 3/4 of it. You know? So you can get around this problem of polyalkylation, but you're not going to want to do that at a late stage in synthesis. You're not going to use a whole bunch of excess of a highly decorated benzene ring just so you can avoid the polyalkylation problem. Another issue with this. And this goes to the question that was asked a minute ago. Let's see if, remember what our reactive species is here. We wouldn't really have to worry about anything with the ethyl benzene, but let's say we were trying to make propyl benzene. If we were trying to make propyl benzene, presumably, we would use chloropropane, the Lewis acid. The reactive intermediate that would generate would be that. Does anybody see a potential problem with that carbocation? Yeah, exactly. Remember, anytime you're dealing with carbocations, you always have to be on the lookout for rearrangement. Do you see how if you made that primary carbocation, that it could make a more stable carbocation simply by doing a hydride shift? The hydride shift would take that from a primary carbocation to a more stable secondary carbocation. And if it did that, then your product would not be propyl benzene, but instead isopropyl benzene or cumene. So you have to be on the lookout for carbocation rearrangements here. When a carbocation can rearrange to make something more stable, it will rearrange. All right. Any questions on this one?
What if we want to make a propyl benzene? We cannot.
Hold on to that question because we'll address it in the part B of these Friedel-Crafts reactions. We'll get to that in just a second. Okay, a third limitation is you can't do this reaction with strong electron withdrawing groups on the ring. All right. The whole point of that is think of the first step of the mechanism. We're relying on electron density from the pi system to go out and attack an electrophobe. So if you have really strong electron withdrawing groups on the ring, it's a very, very deactivated ring. There's just not a lot of electron density in the pi system for it to go and attack something. And so the usual suspects here for strong electron withdrawing groups are going to be nitro groups, sulfonic acid groups, and probably the most limiting, carbonyl groups. So for instance, if you had benzaldehyde and you were trying to, let's do the same reaction. Trying to do the Friedel-Crafts alkylation to put on an ethyl group onto this ring. This reaction would fail because you cannot do these Friedel-Crafts reactions with those strong electron withdrawing groups on the ring. Okay. Any questions about these limitations? All right. Well, Friedel and Crafts were no idiots. They recognized that their reaction had some pretty significant limitations. And so they took a second bite of the apple. And what they came up with was come think of it as a version 2.0. And these are called the Friedel-Crafts acylations. So instead of putting an alkyl group, we're going to put on an acyl group. All right, and what that looks like so we're still using the Lewis acid catalyst, but in this case, we're not going to use an alkyl halide, we're using an acyl halide, and what that looks like is this. So you notice the only difference is that instead of the halogen being attached to an alkyl carbon, it's attached to a carbonyl carbon. All right, and that's what I mean by whenever I say an acyl group. Mechanistically, it's pretty much the exact same though. The point of the Lewis acid is to pluck the halogen off. And if we do that with these acyl groups, we end up with something that looks like this. So we make this ion here that's termed an acylium ion. And this guy is resonance stabilized. Like so. But again, mechanistically, there's no real difference. The pi electrons are going to go out and attack the electrophile. Generating the high energy sigma complex. And then the conjugate comes in to grab the proton and restores the aromaticity. And it transfers that acyl group onto the benzene group. So how is this better? Well, so we said there were three significant limitations to the alkylation reaction, namely the polyalkylation, carbocation rearrangement, and the no strong electron withdrawing groups. Well, have a look at the reactant and the product pair. We've got regular benzene and then this acylated benzene. Which of those two rings is more electron rich?
Between which two?
Which one?
Between which two?
The benzene or the acyl benzene?
The acyl.
Well, we're putting on a carbonyl group
it
onto
takes
the
it.
ring in this case.
It takes it, yeah.
Yeah, remember the carbonyls are one of those really strong electron withdrawing groups. And so by putting on the acyl group to the benzene ring, we're making this guy much more electron poor than it was to begin with. So that first problem of polyalkylation, we really don't have to worry about. I'm gonna call it polysubstitution because it's not technically polyalkylation in this case. Because the product is more electron poor than the reactant. The second problem we had were the carbocation rearrangements. Well, we're not making a carbocation in the classic sense. Right? Instead, we're making a resonance stabilized carbocation. So because we're generating a resonance stabilized carbocation, there is no carbocation rearrangement. Now, unfortunately, the third limitation still applies. You cannot do the alkylation or the acylation with strong electron withdrawing groups. And again, it's going to be those usual suspects: nitro, sulfonic acid, or carbonyls. Okay, that one still holds. But 2 out of 3 ain't bad. So I've kind of, let me go on to the third kind of permutation of this, and then we can talk about the similarities between the alkylation and acylation. So if I were to ask you, let's make benzaldehyde. You know, benzaldehyde looks like this. By analogy, we should be able to just do Friedel-Crafts acylation on benzene. I guess in this case, where we came from, we made the 2-carbon acyl benzene using the 2-carbon acyl halide. So kind of by analogy, if we wanted the 1-carbon acyl benzene, we would use the 1-carbon acyl halide. Presumably we'd do something maybe like this. And that makes perfect sense. The only issue here is that this is called formal chloride, and it's very unstable. You can't just go buy a bottle of formal chloride. All right? So what that means is you have to make it in situ. You have to combine a bunch of things in the flask in order to make it, and it gets consumed as soon as it's made in the flask. So the way we do this, I'm going to call this 4C. It's technically a Friedel-Crafts variant, but it's given its own name after the people who discovered it. But this is called the Gattermann-Koch reaction. And the way they get around that formal chloride thing is they make it in the flask through a combination of carbon monoxide, copper chloride, hydrochloric acid. Those 3 things make formal chloride. And then the only other thing we need is the Lewis acid to put it on the ring. that's how you would make benzaldehyde. Benzaldehyde, as it turns out, is a very useful tool in synthesis. You know, again, it would be a very nice way of adding benzene rings into your compounds because it would be a substrate for a Grignard addition. All right. Any questions on the acylation or the Gatterman-Koch?
So what's the difference between the Gatterman-Koch and the example above?
Not really anything other than the Gatterman-Koch is a specific variant of the acylation. So you're only ever going to use this to make benzaldehyde. The Gatterman-Koch can only make benzaldehyde. The Friedel-Crafts acylation can make any acyl benzene you could ever want.
So the formal chloride, right, you said you make that in like a beaker or something?
Yeah, so, well, you don't really make it in a beaker. You just you would take the benzene, you would add in your copper, your HCl, and whatever solvent you were using, and then you would bubble in carbon monoxide, or you could actually just drop dry ice in there too, but along with the Lewis acid. So you combine all of this stuff in the round bottom flask, and it makes the formal chloride kind of in the flask, which immediately gets consumed as soon as it's made. Okay, any other questions on those? So I kind of build the acylation as a better version of the alkylation. But is it a direct substitute? You know, let's go back to the question a minute ago. What if we wanted to make propylbenzene? You know, I already showed you that you cannot say we wanted to do this. We already discussed how you could not use Friedel-Crafts alkylation for this. Due to the carbocation rearrangement, you would end up making the isopropyl benzene. Okay, well, if I can't use Friedel-Crafts alkylation, could I use the acylation? Well, we would start with benzene, obviously. Maybe put on the 3-carbon acyl group, which would give us that. Well, I mean, it's nice that I put a 3-carbon group on the ring, but it's not exactly propylbenzene at this point, is it? The issue is these benzylic ketones that the Friedel-Crafts acylation allows you to make are very, very easy to reduce. So, there's a couple ways we could think about doing this. I can take that benzylic ketone and I can easily reduce it to propylbenzene. And one of the easiest ways is simply through hydrogenation. So you can do catalytic hydrogenation on these benzylic ketones, and it will reduce to the methylene. So this kind of combination of Friedel-Crafts acylation plus reduction does give you a direct substitution of the Friedel-Crafts alkylation. Now, this reaction should surprise you a little bit. Just think back to last semester. If you had, let's just do some regular ketone. If you were to do hydrogenation on this ketone, what did you learn last semester? What kind of functional group would result?
Just leave it in H group.
Yeah, exactly. If you take and you do catalytic hydrogenation on a regular ketone, you get the alcohol. That's what you learned last semester. And the point I'm trying to make is that the benzylic position is a unique position. It doesn't react like normal, well, anything really. So when you have a benzylic ketone, it's going to react differently than if you had a just run-of-the-mill ketone. And you can see that clearly here, where the reduction of a benzylic ketone with catalytic hydrogenation gives you the methylene. The reduction of a regular ketone gives you the alcohol.
So the benzylic position is like right one carbon away from the benzene.
Yeah.
Wouldn't be like 2 or 3, just.
Nope. Yeah, it's analogous to the allylic position. You know how the allylic position is one next to the double bond? The benzylic is one next to the benzene ring.
Are these supposed to be benzene rings or no?
No, not on the bottom.
Okay.
Yeah. This is just some random ketone.
But since it's not in the benzylic position, it's one away, even if it were a ketone.
Yeah.
I mean, even
I
if
could,
it were
I could have,
benzene.
I could have the ketone here, 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 really anywhere. It would not be a benzylic ketone because there's not a benzene ring here.
If it were a benzene ring and it were in that position where you've drawn it,
It would not be a benzylic ketone.
It would still go to OH,
Yep,
right?
yep.
Okay.
So if we had, let's just draw that up. So if we had that, catalytic hydrogenation of that would give us the alcohol,
Okay.
because that is not a benzylic ketone. It is only a benzylic ketone if it is adjacent to the benzene ring. All right. I'll give you a second way to reduce these, the acylation products if you need to. And this is another named reaction. It's known as the Clemenson reduction. The Clemenson reduction will take, by the way, this is a general reduction for any kind of a ketone. So the Clemenson will take a ketone, any ketone, benzylic or otherwise, and it mixes it with a zinc amalgam, which is kind of a zinc mercury couple, under strongly acidic conditions. And it also generates the methylene group. And again, you can do this with any kind of a ketone whatsoever. So if I had, let's look at that same molecule that we used a minute ago. This would also reduce to the methylene. So the Clemenson will work, will reduce any ketone whatsoever to the methylene group, whereas catalytic hydrogenation will only reduce a benzylic ketone to the methylene group. All right. Any questions on this one? So my recommendation for you, as you start to approach your synthesis, is I would recommend using the Friedel-Crafts acylation. The alkylation reaction, as we discussed, has some pretty significant limitations. And so for practical use, I would just recommend using the Friedel-Crafts acylation. It's better in almost all cases. All right. Any questions on these Friedel-Crafts? Okay, then that takes us through all of the electrophilic aromatic substitution reactions. Where we'll finish this chapter up is just kind of random benzene reactions. All right, they don't really fall into any kind of a mechanistic umbrella. They're just kind of random reactions you can do on benzene. All right, so I'm just going to call these other benzene reactions. The first of these is the seemingly impossible. So you can take benzene and under the right conditions, you can hydrogenate it. I know I told you you really couldn't, but it turns out under the right conditions you can. The problem is that if you're going to try to do this under what I would call a normal hydrogenation conditions, say like H2 and palladium, you're going to need roughly 1,000 psi of pressure. That is extreme pressure. And number one, it's very difficult to accomplish. And number two, even if you could, what glassware is going to survive that? So if you're going to try to do catalytic hydrogenation with palladium on benzene, you really need very, very specialized equipment that the vast majority of labs do not have. Right? You're not going to go into room 406 across the hall and try to do catalytic hydrogenation on a benzene. Because there's no way you're going to get to 1,000 psi, and even if you could, we don't have any kind of equipment that could accommodate 1,000 psi of pressure. So there's that. You can get around this very high pressure situation if you start using more exotic transition metals. So for instance, if you, instead of using palladium, you use something like rhodium or ruthenium, you can do this at effectively atmospheric pressure. But that's also a little problematic. I don't know if you've kept your eye on the price of rhodium lately, but just as kind of a matter of comparison. So, gold is obviously a commodity, and the price of gold usually fluctuates somewhere between $1,500 and $2,000 an ounce on the market. Rhodium is also a commodity, and it's traded like other metals. Over the summer, I haven't looked at it lately, but over the summer, rhodium was trading for over $27,000 an ounce. So, you can, in theory, use these exotic transition metals to affect your catalysis. I guess if you got somebody footing the bill, $27,000 an ounce is not exactly chump change, to me anyway. But, so you see the problem here. With the hydrogenation of benzene, you either need extreme conditions of pressure or to be filthy rich. Now, in your synthesis, that's the nice part about paper chemistry, right? We don't have to be concerned with the limits of reality. So if in a synthesis problem, you want to use catalytic hydrogenation of a benzene, more power to you. Use it all day, every day. Just be aware that if you were to actually try to plan this to do it in person, this reaction would be a little bit difficult to achieve. But for paper chemistry, why not? You know, use it all you want. Any questions about the catalytic hydrogenation here? Okay, the second one we'll look at is what's known as side chain oxidation. This one is a little bit limited because it will always only ever make one product. So you can take these benzene rings that are alkyl substituted, treat it with permanganate, and this will always give you a benzoic acid compound. Now there is a little bit of a caveat here. In order for this to work, the benzylic position must have at least one hydrogen. So for instance, if I were to ask you about this reaction, could you predict the product of this side chain oxidation? Would the methyl group oxidize? Yeah, it should. It would oxidize to give a benzoic acid derivative. Would the isopropyl group oxidize? The only requirement is to have a benzylic hydrogen. Does that benzylic carbon have a hydrogen on it? Yeah, it does. And so it would oxidize. And what about the T-butyl group? No. It does not have a benzylic hydrogen. This carbon is surrounded by nothing but other carbons, and so it would not react. It would remain untouched.
So in the isopropyl group, we lose one carbon.
Yeah, you're always cleaving anything that's attached to the benzylic position, no matter what it is. So that's why I say it's a little bit of a limited reaction because the only thing you can ever get from it are benzoic acid type structures. Okay. Any other questions on this one? Mm-hmm.
So the isopropyl has 3 carbons, what happened to the other one?
They just get cleaved off. Everything beyond the benzylic position gets cleaved off as carbon monoxide, probably carbon dioxide.
Like a physical
Kind of, yeah, kind of the same thing. Okay, so I think we have time for one last, at least part of one last one. Well, the second reaction I just gave you, the side chain oxidation, is a little bit limited. I don't know how much you'll actually use it in your synthesis. This next one is incredibly useful. And it is benzylic bromination. So if you remember, This is gonna be very similar to something you've already learned, right? Back last semester, you talked probably fairly extensively about the allylic bromination. Well, this is a very related reaction. So I can take something like this. Do you remember what was the reagent that you used for allylic bromination?
NBS.
Yep, NBS. So that is oftentimes used here as well, but not exclusively. So if you recall, with the allylic situation, the reason why you typically used NBS was because you wanted to ensure the allylic bromination. You know, if you were to use just regular old bromine for this, depending on how you run the reaction, you can get allylic bromination with molecular bromine. That is possible, but you have to monitor the reaction extremely closely. It's a concentration thing. If the concentration of bromine is very, very low, you'll get allylic bromination. But if it reaches above a certain threshold, you end up starting to add bromine across the double bond in an addition style reaction. So that's the reason why most people, if they're gonna do an allylic bromination, they'll choose to use NBS, because that's something you just throw in the flask and walk away. You don't have to, you don't really have to do any work. Using bromine under these conditions in order to achieve allylic bromination, you really have to monitor quite closely. Would you have to worry about benzene undergoing normal addition with Br2? Like, would I have to worry about this happening? No, that's never gonna happen. Because again, you're not gonna lose the aromaticity of the benzene ring. So it doesn't really matter. With benzylic bromination, use whatever you want. You're only ever gonna get the one product. You're only ever gonna make a benzylic bromide. You're never gonna have to run the risk of bromine adding across these double bonds. Okay, so I think that's probably a good place to stop. We'll pick up here on Wednesday, and we'll look at why benzylic bromination is useful, but I think that's probably about all we have time for right now.